Hello everyone, my name is Sarah Levrey. I work for Areva Cogeneration as research engineer. I am also a PhD student at the University of Corsica in France, supervised by the Professor Christian Cristofari and Dr. Lingaio. This thesis is funded by Areva, but I work at the MYRTE platform in Ajaccio with the team of the university. My research topic is exergetic optimization of an hydrogen chain operated in cogeneration application for the MYRTE platform. MYRTE is a research platform composed of photovoltaic panels and a hydrogen chain. So I'm going to explain the current situation. Corsica is a French island located between France and Italy. Fuel-fired thermal plants generate the majority of power production in Corsica. The rest is produced from renewable energy, like hydraulic one, and especially from solar energy. Indeed, in Corsica, the solar potential is high with 1,500 kilowatt per square meter per year of solar radiation and around 2,860 hours of sunshine per year. That is why there are a lot of photovoltaic plants. But solar energy is an intermittent resource. The production is not constant over the time. It depends on the hour and the month. So sometimes the production is too high, sometimes too low. That is a big issue for the electric grid operator. Due to this intermittence, it is very difficult to assess the production grid stability. That's why in France, the rate of power from renewable energy in the energy mix is limited to 35%. However, this rate is already reached in Corsica. In order to use even more renewable energy and to ensure the grid stability, an energy storage system is required. Many ways are possible, but we have chosen an hydrogen energy storage. Indeed, hydrogen has a high energy content, is non-pollutant, and can be used for many applications. Currently, only few pilot platforms have this kind of installation. The main objective is to improve the performance of the hydrogen chain in order to make it profitable and to promote this system. So, what is an hydrogen chain? Hydrogen chain is composed of an energy sources. In our case, we only consider renewable energy, but it is possible to use fossil resources if there is a process for carbon captation, as we can see here. The surplus of energy is converted to hydrogen and oxygen in an electrolyzer. Hydrogen is then stored either in form of gas or in form of liquid, mostly is in form of gas in high pressure tanks. Then hydrogen can be either transported for further application, or another way is to use hydrogen on site to regenerate power like in MYRTE platform. So the hydrogen chain is very interesting for stationary application. So we need an renewable energy source. And here hydrogen chain is also composed of an electrolyzer and a storage system. Different technologies of electrolyzer are available, like alkaline electrolyzer, proton exchange membrane electrolyzer, and solid oxide electrolyzer. When we need power, hydrogen is fed into a fuel cell where power is regenerated. So several technologies of fuel cell exist. Most used are alkaline fuel cell and proton exchange membrane fuel cell, but a lot of research are ongoing, especially on solid oxide fuel cell, which can be operated at high temperature. The other are phosphoric acid fuel cell, direct methanol fuel cell, and molten carbonate fuel cell. Finally, power can be fed into the national or local grid. Another very interesting way is to use a cogeneration module in order to produce both heat and power. The heat recovery allows to significantly increase the global efficiency. So, hydrogen can be used in many ways. Hydrogen can be sold to industries. Here, hydrogen is then used as raw material in many industrial sectors, for example, for the ammoniac production, glasses production, or for the production of textile fibers. It is called power to feedstock. In the industry, hydrogen can also be used as fuel to power engines. Hydrogen can also be used as fuel for the mobility sector. It is the power to mobility. It already exists hydrogen-powered buses and cars. Another way is for the energy sector, of course. Either hydrogen is converted to power, as explained, and is it power to power, or hydrogen can be injected into the national gas grid or used in methanation unit to produce methane, which is also injected into the national gas grid. So this is the power to heat or power to gas. Also, hydrogen offers a wide range of applications. But currently, hydrogen energy storage systems are still unprofitable. The cost of hydrogen production is still high because the different components are expensive and need some improvement in terms of reliability and efficiency. Currently, the efficiency of an hydrogen energy storage system is around 40%. However, to increase the overall efficiency and to reduce the cost of hydrogen, one solution is to use hydrogen in different ways. For example, one part of hydrogen production for mobility, one for the power generation, or another part for the national gas grids. When the use of hydrogen are various, the overall efficiency is higher. I would like to recover the heat produced throughout the system in order to operate the MYRTE platform in cogeneration mode. As we can see, heat is producing in the electrolyzer and in the fuel cell. Currently, the heat is wasted, but I would like to use it for hot water production, for example. And cogeneration increase significantly the efficiency over, so the efficiency is reached over 80%. In the hydrogen energy system, there are different nature of energy flow, as we can see, electrical flow, hydrogen flow, and heat flow. It is not easy to compare different nature of energy, and also it is difficult to determine which operating mode of the platform is the more efficient. So how can energy flows can be best and optimally managed? So to manage this energy flow, I decided to use a new approach, so the Exergetic analysis. The first step of my work is to consolidate the existing static and dynamic characterization of each platform subsystem, first through an energy analysis and then through an exergy analysis. So energy refers to the quantity of energy, while exergy to the quality. Exergy can be defined as the useful potential of a certain amount of energy at a specific stage. Contrary to energy analysis, in the exergy analysis, we take into account the reversibility of reaction. We consider the first and second law of thermodynamics. The objective is to model exergy destruction and losses of each unitary operation in order to minimize them. Here is the general equation of exergy. Exergy analysis allows to identify where, why, and how much energy is wasted, and to quantify the rate of irreversibility due to the entropy generation of each component. The second step is to develop an energy management system to manage the entire platform and to allow an analysis of thermal potential and of the electrical constraint of the platform. This energy management system should be able to optimize the state of charge of hydrogen over several days. Last step is to find the best case for which the value addition of such a system. It consists of studying various operating scenarios and to determine the best under technical and economic criteria. So I'm going to introduce you the MYRTE platform. MYRTE, result of a partnership between Areva and the University of Corsica. MYRTE is composed of a PV photovoltaic area of 560 kilowatt and 2,240 units. Behind them, we have the process area, including electrolyzer and fuel cell. And then we find the storage area. So hydrogen and oxygen are stored under 35 bars. The storage capacity of hydrogen is 2,000 cubic meter. The process area is divided into two sections. The holder is the section 1, which is composed of 50 kilowatt electrolyzer, produces 10 normal cubic meter per hour, and of 100 kilowatt fuel cell. The section 2 is called the green box and is composed of 57 kilowatt electrolyzer and 50 kilowatt fuel cell. All components are in a container, so allowing to transport and install the green box easily and quickly everywhere. The both electrolyzer use PEM, proton exchange membrane technology, as a fuel cell. In order to operate the platform in cogeneration, the heat management system is essential. Its main goal is to cool the process, namely the electrolyzer and fuel cell. It is composed of two heat exchangers for cooling electrolyzer and fuel cell, in which circulate a glycol water mixture and a dry cooling system. It is also composed of one heat exchanger for heat recovery and two heat storage tanks. Seven operating modes are possible. The first mode is when the entire system is off. Mode 1 allows only to cool the process. The mode 2 allows to cool the process and to recover the heat. Heat in this case is immediately used. In the mode 3, the heat recovery, the recovered heat is stored in order to be used later. The mode 4 consists of using the heat stored in the tank. The mode 4 and 1 is a combination of mode 1 and 4. At the same time, but independently, heat storage is used in the heat exchanger for recovery, while the feed of process is cooling. The last mode is the purge. With this system, we can operate in different ways according to what is needed at a specific time. It's needed. Currently, the energy analysis of the platform is almost completed. To summarize easily and quickly with periodic equation, modeling and simulation of the electrolyzer depend on 5 parameters: the charge transfer coefficient at the anode, the current density, the activation energy required to transport electron to the anode, the protonic conductivity of the membrane, and the activation energy to transport the protons in the membrane. These parameters are obtained from the experimental polarization curves. Fuel cell energy balance is similar, but we focus on the cathode. The thermal model of fuel cell depends on the heat capacity of the control volume and the thermal resistance, and the storage system depends on the number of moles, the pressure, the temperature, and the volume. Each component of the heat management system has also been modeled. Here are the equations. All models of each component have been tested under several conditions. All mathematical models simulate properly the equipment. The platform model is validated. So, however, there is substantial work to be done. From energy analysis, the exergy analysis will be quickly started. The higher heating value of hydrogen, which is usually used, will be replaced by the exergetic value. According to the result of exergy analysis, we will determine the operational scenario, which can be interesting on the MYRTE platform. And the last but not the least, the last step is the development of an energy management system. So there is still a lot of work, but the first results are promising and could help to achieve the objectives of the energy transition. Thank you for listening.